Hi and welcome everyone. In this lesson, we will talk about two important or two critical factors that we are going to use in the load estimation part of the course in the panel schedule. These factors are very important because they will affect the selection of circuit breakers, selection of cables, and they will also affect our load estimation process. So let's start by talking about the demand factor and diversity factor. So first, in order to understand this, let's talk about our electrical system. So let's look at this image here. This is part of AutoCAD drawing that we will see inside our course. This representing a part of our apartment. This apartment here, or this drawing here, representing what? Let's type it with our pencil. This one representing an apartment. Okay, this drawing here representing the power circuits. So we will learn inside the course, after learning about lighting design and etc., we will find that we have electrical drawings for lighting circuits, one drawing for lighting circuits and another one for power circuits. When we say power circuits, we are talking about the power outlets or power sockets, and we also talk about the electrical heater, the split air conditioning system, and etc. So what you can see in this image here on this drawing, AutoCAD drawing, part of the apartment, you can see we have this room, this one, and we have another room here and the rest of other room. You will see this shape here, this one representing our electrical panel. Okay, that you will see in any apartment. If you look at near the entrance of any apartment, you will find here a panel board like this, contains a group of circuit breakers like this, which you can switch on and off. Group of circuit breakers. Now each of these circuit breakers will go to a certain circuit. It can be a lighting circuit which provides electrical power to group of luminaires, and it can be a power circuit which provides power to air conditioning, power to group of sockets or outlets, and etc. So this is our distribution board that will give electrical power to all of these sockets. This symbol here representing our normal socket. Like what exactly is this normal socket? Like this. Let's just delete all of this. Like this one, you can see this power outlet that you see in the walls. This power outlet, we call it normal socket. This one has this symbol. So this one here, this representing one power socket on this wall. If you look at this room, you can see power socket here. Then after a certain distance, another one, another one, another one, another one, and etc. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These 10 sockets are connected together. You can see this wiring between them. It means that they are connected together, or taking the electrical power from the same circuit breaker, or from the same line, same circuit. You remember that our distribution board consisting of group of circuits. One of them is this one. You can see this is the name of the circuit. Okay, we will learn about this when we go to how to add sockets in our drawing, how to draw the luminaires, how to wire them. So don't worry, I'm just explaining this because we are going to talk about demand and the demand factor and diversity factor. So this is important in understanding how it works. Now we have the first definition, which is called the connected load. This is the summation of all of the loads in the electrical system. So we have, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These sockets, let's say they have a power of, let's type it here, 2000 volt ampere. Now I'm going to ask you, are these sockets, are all of these sockets, are used in the same time or not? Are they will be used in the same instant or not? Actually, in reality, they are not going to be used in the same time, because if you look at any room or any apartment, you will never find these sockets working at the same time. I can, for example, connect here my own charger for my mobile phone or for my computer, okay, and the rest will be not used, right? Another way, I could be connecting here a refrigerator, for example. I can be connecting a microwave and etc. So not all of these sockets will be used at the same time. That's why we have, not all of these are operating. That's why we have, when we design, we have to consider something which we call the demand factor. Why demand factor? Okay, now remember, if we design our let's say 2000 volt circuit number one, then I'm going to choose a cable that will be able to provide 2000 volt ampere or the equivalent current, and I will choose a circuit breaker that will also withstand this value, right? However, this will lead to higher cost of the system, since I'm selecting an oversized breaker, oversized cable for the circuit here, because in reality they are not going to be working at the same time. That's why we have demand factor. We take this value and multiply it by certain value, let's say 80%. What does 80% mean? It means that only 80% of these sockets will work, right? Not all of them, just 80% of these sockets. Now in this case, you will have a lower value, which means lower circuit breaker size, lower cable, leading to lower cost. So let's identify or provide the definition for the demand factor. So this demand factor is actually applied for what? Applied for lighting circuits and power circuits. Power circuits like this one. And for lighting circuits, for example, you will find that in this room, let's say we have 1 luminaire, 2, 3, and 4, 5, 6, 7, 8, and here, for example, all of this, for example, connected like this together. So not all of these will be working together. So we have also a demand factor for lighting circuits. So this, when we do the panel schedule, we will have to multiply this by demand factor, since not all of them are working at the same time. So what is exactly the demand factor? Demand factor is simply the maximum demand of a system divided by total connected load on the system. So what does this mean? Let's say we have an apartment with a total connected, all of the luminaires plus all of the sockets, everything in the apartment. Let's say it is equivalent to 10 kilovolt ampere. However, this apartment will have a maximum demand, maximum amount of power taken. Let's say it will be 7 kilovolt ampere, because not all of these loads in our apartment will work at the same time. So it will be 7 divided by 10. So our demand factor is 0.7. So only maximum demand, maximum amount of loads that will be working at the same time will be just 70% of the total load. That is what we call demand factor. Now in lighting circuit in my design in this course, I assume 100% demand factor, and for power circuits I assume 85%. And what I say about power circuits, I'm talking about normal circuits here. For air conditioning and for electric heaters, I assume 100% demand factor. Now these values can change from one code to another, from one country regulations to another, from one standard to another. For example, you will find in IEC values different from NEC, different from IEEE, and so on. So depending on what standard you are following, you will design based on it. Okay, so I'm giving you the outline or the plan which you are going to follow, or the steps you are going to follow, and based on what code you are following or electrical code you are following, you will do these steps. As we said, these values are critical when we select cables and breakers. Now the demand factor in IEC, so we have demand factor in general, this is a term that I'm talking about. In IEC you will find it factor of maximum utilization and denoted by KU. So in IEC, if you are looking for demand factor, you look for factor of maximum utilization. This is exactly this one, but in IEC it is written in a different form. Now also in mechanical systems such as HVAC system and so on, the mechanical engineer can give you values of utilization. We have utilization factor for machines. Okay, so this values similar to demand factor in electrical system. However, the demand factor, this utilization factor will be given by mechanical engineer. If you don't have it, you assume it with unity. Okay, now usually demand factor is less than or equal to 1, as we have seen here, because it is maximum demand which will never exceed the total connected load. Now this is also, again, what I have just said is that this demand factor is considered for main loads such as lighting, air conditioning, and sockets. That's why you will find in the panel schedule that we will learn in the course that I select lighting as 100%, air conditioning as 100%, and sockets as 85%. So we have here lighting. If we look at this panel schedule that we will learn inside the course after designing our circuits for lighting, for power, and etc., you will find we have these loads and their equivalent connected in kilowatt. Here we have them in kilowatt, and we will divide each by power factor to convert them. So we divide, let's say for example, if we would like to get this lighting in volt ampere, because we are dealing in the end with volt ampere, we take the connected load 1.2 divided by its power factor 0.8. So it will give us how many volt ampere. This is our connected load. Okay, summation of all of the power of the panel of the lighting circuits, all of the power of the lighting circuit, and then divided by 0.8 to convert it into volt ampere. So this is the maximum or total connected load. Now lighting circuit, we will divide it by DF or demand factor, which is 1 or unity. So we take this and multiply it by 1, give us how many kilovolt ampere, which is 1.5, which is exactly this. Now similarly for sockets or the outlets, here you can see we have all of their power 7.7 divided by 0.8 power factor, you will get connected load, then multiply by demand factor of 0.85, you will get how many volt ampere, right? Similarly, in the end, you will find that we have how many kilovolt ampere, and in reality, the total connected load is 25 kilovolt ampere. So the total demand factor is just 95%, very close to unity. Okay, now what? So we now have this value. What does this value we call? We call it the demand load. Okay, not the connected but demand load. This is the value of our panel. Now the next step, you will have this riser of the building. We can have a single line diagram and we will have riser of the building. What does riser of the building mean? We have this building, which is a building with 4 floors in addition to the ground. Okay, now in this building we have 2 apartments in the ground floor, and we have in each floor 2 apartments. So you can see this is our ground floor. We have 1, 2, each of these representing panels. Let's say magnify. You can see here this and this one and this one, each of these representing what? Representing a panel, such as the panel which we talked about, 25 kilovolt ampere, 25 kilovolt ampere, the one which I'm just talked about, okay, which is the 24 kilovolt ampere, the demand value. Okay, each panel representing demand load. Okay, so we have 1, 2 apartments, and then on the first floor we have an apartment on the right side, apartment on the left side, another one here, another one, and etc. Now you can see we have main distribution port. This distribution port, which can be at the entrance of the building itself, it is used to provide electrical power to what? To these panels, right? Go from here and go to this panel and this one. Then we have this riser, a 3-phase going up to the 4 floors to provide electrical power to these 4 apartments, and another riser going to the building and supplying electrical power to these loads or these panels. Okay, so we have how many panels? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 distribution panels. Now I would like you to think carefully. Are these apartments will work at the same time, or they will not work at the same time? They will not work at the same time. Not all of these apartments will have the maximum demand at the same time. That's why we will have to apply another factor. This factor is called the diversity factor. Diversity factor representing the diversion between different loads. Diversion between different loads. So the demand factor is applied between similar loads, such as lighting circuits demand factor, power circuits demand factor, air conditioning demand factor, and etc. For the loads for different panels, different distribution board, we apply what we call the diversity factor. Okay, this will help in sizing our transformer and sizing our cables here. Okay, under size. Okay, now after this step we will have a large group of panels. We will take those panels and multiply them by the coincidence factor or divide them by the diversity factor to get the coincident load or the diversified load. Okay, what is the difference between them? Nothing different. In different codes they say we have diversity factor, which is exactly in other codes like IEC, they call it the coincidence factor. So what is exactly the diversity factor? It is the ratio of the sum of all of the individual maximum demands. You have here all of these panels, 25, 25, 25. Add all of these, we have 10 apartments, so we will have 10 multiplied by 25, since each one is 25 kilovolt demand load, not connected demand load, so it will be 250 kilovolt ampere, right? Like this. Okay, Now what? Now we have 250 kilovolt. This is the maximum summation of all of the individual maximum demands of the various subdivisions of the system. To what? To the maximum demand of the whole system. Now all of these panels will not have the maximum demand at the same time. So let's say this system will have a maximum demand, the maximum time at which all of these will take power. Let's say it will be 100 or let's say 200. So that is the maximum demand of the whole system. So it will be what? It will be 250 divided by 200. It will be 1.25 if I remember correctly. Okay, so always the diversity factor is always greater than 1. Greater equal to 1 or greater than 1. Demand factor is lower than 1. Okay, so in order to get the power of this distribution panel, it will be total demand, which is 250, divided by the diversity factor, okay, to get 200, which is the lower number. In other codes, we have coincidence factor. Now, coincidence factor or simultaneous factor or simultaneity factor, all of this representing the same, it is exactly equal to simultaneity factor, or the coincidence factor is equal to 1 over the diversity factor. It is the reciprocal of diversity factors. That's why these factors are less than 1. That is the correct definition of all of these. Now, in different codes, you will find that in some countries, you will find that demand factor is treated exactly as diversity factor. In other codes, they say they treat diversity factor as less than 1, as if it is a simultaneous factor. So depending on what value is given, I will be able to design my system. You will see what I mean in the next slides. So you see, in diversity factor in IEC, they call it the simultaneity factor or coincidence factor, which is the inverse of diversity factor. You will find this factor if you would like its values in IEC 61439. And it is always greater than 1. Now, the demand factor by experience, usually by experience, without codes, we usually find that in lighting we use from 0.9 to 1. For sockets it will be from 0.5 to 1. For air conditioning between 0.75 to 1. And demand factor, before we go to this, demand factor, this is according to our experience, okay, in from different projects that we have done before. However, if you would like to follow the codes, look at the next slides. Number 1, for IEEE. For IEEE, here it gives you the connected load and the maximum demand load. Here, how many watt per feet square. So if you have a shoe store or a department store or drugstore or whatever, restaurant, so what I'm going to do is that if I would like to know the load of that restaurant, so what I'm going to do, let's say I have let's say how much, let's say 1000 feet square, let's say 1000 feet square restaurant, and I would like to know its load, okay, 1000 feet square restaurant. How can I get its load? You can see connected load, watt per feet square, watt per feet square. So I'm going to say, go to restaurant and 15.9. So its connected load will be 15.9 watt per feet square. So what I'm going to do is that I will take this value and multiply it by the space of the restaurant. It will be 1000 feet square. It will give us 15.9 kilowatt. That is the connected load of our restaurant, and since all of these loads are not going to work at the same time, then the demand factor, according to IEEE, for this application restaurant will be 0.45. So when I design my panel, or when I design my transformer for a building consisting of a restaurant, for restaurant alone I would take this load and multiply it by 0.45. Okay, to get what? To get the demand load. That's how you can apply this. Now another thing, this table also can be used for load estimation, for estimation of the load in the building, restaurant, bakery, candy shop, and etc. We will see how can use something like this in the next lesson of the load estimation. Now demand factor according to the NEC. So the NEC say that if you have a lighting load, demand factor. So if you have a dwelling units and its power in volt ampere for lighting loads is 3000 or less, take it at 100% demand factor. So what does this mean? If you have a dwelling unit, its power, let's say 5000 volt ampere, okay, load of lighting, I would like to know the demand factor. It says what? Hey, if you have 3000 or less, first is 3000 or less than 3000, take demand factor as 100%. So this 5000 can be divided as 3000, first is 3000 plus 2000, right? So first 3000 multiplied by demand factor 100% multiplied by 1. Then it says from 3001 to 120 use demand factor 35. So that is the rest higher than 3000. Okay, so it will be plus 2000 multiplied by its demand factor 35. So it will be 0.35. You will get what? Demand load for lighting. So this can be used in designing our panel. So you can see that in the panel schedule or in the beginning of the lesson, I used lighting as a demand factor of 100%. If you would like to follow the code of NEC, then using these rules for a dwelling or a residential apartments, you will be able to design the lighting circuit correctly and specifically according to the code, okay, by using these rules. Now if you have a hospitals, hotels, warehouses, storage, all of these, then follow these according to power rating for lighting and demand factor. Very easy, right? Following the code. Now this is not only the part in NEC, there is more related to different loads in NEC. So in NEC I'm going to leave you a PDF file containing the demand factor for NEC. Okay, now what about the simultaneity factor or the coincidence factor, which if you don't remember, it is the reverse of diversity factor. Okay, this is from IEC 61439. You can see here simultaneity factor for distribution boards. Here if you have how many circuits, 2 and 3, between 2 and 3, take the factor as 0.9. Between 4 and 5, take it like this. Between 10 and more, take it like this, and etc. For lighting circuits, hey, if you have a lighting circuit, take it 1. If you have a heat and air conditioning, take it 1. This is what we have used. In outlets and socket outlets, you can see here it is very small, 0.1 to 0.2. And it says that if you are in industrial installations, factory, for example, then this value will be higher. For us, we selected between 0.5 and 1, and in the course, I selected as 85%. This exactly similar to the demand factor that we talked about from IEC. Now, what about this? This is very important as it will help you in doing this. This is one of the projects that we will discuss in the course. We have a large area. This area consisting of several residential buildings. We have administration building. We have a factory. Okay. Now all of these, let's zoom in. You will see how to do this in our course. Magnify from here. So you can see this one. We have how many distribution ports? 1, 2, 3, 4, and 5. So we have 5 distribution ports. Each of these representing what? Demand load or diversified load. If we are talking about each of these after applying the diversity factor in each building. So if you remember, in first building we had 250 kilovolt ampere, for example. And then after applying a diversity factor, we obtained 50 kilovolt ampere or 150 kilovolt ampere, whatever it is, depending on what project we are dealing with, as we will see in the rest of the course. But anyway, we have this distribution port, main distribution port for the building. All of these ports are taken from a transformer connected to the power grid. Great. Now these are 297, 225, 500. Now of course, since we have group of panels, then we will apply a diversity factor. Other codes, they consider diversity factor as demand factor. So here you can see it is demand factor 80%. We can say, for to be more specific, diversity factor, or to be more specific, coincidence factor. Because here you can see that according to this, you can see here, if you have between how many circuits or how many feeders or how many distribution ports, if you have between 4 and 5, take it 0.8. So if you look at here, we have 1, 2, 3, 4, 5. So we took it as 0.8. This one representing the diversity factor or the simultaneity factor, to be more specific. Okay. Now remember, there are some codes that they consider these are diversity factor, even if we know that diversity factor is greater than 1. However, some codes confuse it and use it as less than 1. Okay. Now here is another one. You can see here, we can see from IEC, it's called what? Simultaneity factor less than 1. You can see here in IEC. Okay, here you can see diversity factor. This is obtained from what? From the French code. You can see here, this one from French code. Both of these French code following the IEC, they have the same one. This is from Schneider Electric, and according to them, this is also obtained from French code that is based on the IEC code. Okay, but they say diversity factor is, except that despite that we said before that diversity factor is greater than 1. But anyway, neglect these definitions. You already know that diversity factor greater than 1 and simultaneity factor or coincidence factor less than 1. That is the correct definitions. However, in the end, what we call it, we will use these values in design. Let's see how. So we have this these panels. You can see one panel, another panel, and another panel. This panel provides electrical power to 2 panels. Then between them there will be diversity factor, right? Now this panel provides for 3 consumers. This one provides for 4 consumers. Then between these we will have a diversity factor, and between these we will have diversity factor. So you can see at each level or at each stage we add diversity factor. Now in the end, this depends on what? Depends on the code you are following. Some codes say, hey, don't do this, don't add diversity factor here. add it at the transformer part. Hey, other code will say, hey, at every stage add the demand factors and add diversity factor. Okay, so it depends on what code you are following. Let's say for this example here, what we are going is that first we have 3 consumers. Between them there will be diversity. So diversified load of first panel, this one will be total load 10, 11, 12 divided by 1.11, which is the diversity factor. Okay, so we divided by the great number or multiply by a number less than 1. So we have how many panels? 1, 2, 3. So according to the IEC, how many panels? 2 to 3. Use this one. If you take this is 1, this is what? This is less than 1, so it will be simultaneity factor. So what I'm going to do, take 10 plus 11 plus 12, which will be 33, and multiply it by simultaneity factor, 0.9. Okay, or take the 33 and divide it by diversity factor. So what is diversity factor? It is 1 over coincidence factor, which is 0.9, 1 over 0.9. So 1 over 0.9 will give us 1.11, which is this value. Okay, like this. So this will give you 29.7. If you would like diversity, then divide by 1.11, give you the same value. Okay, now what about for the other sec? We have 1, 2, 3, 4. 4 and 5 use 0.8. So 0.8 for simultaneity factor or coincidence factor. For diversity, it will be 1 over 0.8, which is 1.25. So it will be total connected load divided by diversity factor, or total connected load multiplied by the coincidence factor. Both of them are the same. Anyway, in order to avoid any confusion, all you have to do is take the total load and multiply it by a number that will make it smaller. That's it. Okay, we are trying to make this number smaller. That's all what we do. So we have these two loads and we have diversity between them of 0.9, which is 1.11 again. So we will have 42 kilowatt power rating of this panel. Another one here, simultaneity factor, KS, coincidence factor, IEC, same one. We have this part. This is from the French code. You can see French standard. Okay, this part is applicable for apartments without electrical heating. Without electrical, this is very important. Okay, now you can see the same table here. You can see the diversity factor used in French standard. Here in the IEC, they say simultaneity factor, which is the more correct term. Now, how many customers we have? Between 2 and 4, use a value of 1. Between 5 and 9, use 0.78, and etc. So you can see here we have this example. Let's do this in the next slide. So we have this example on simultaneity. So we have these floors: ground floor, floor 1, 2, 3, and 4. We have here 6 consumers. We have 4 consumers, 5, 6, 4. Now, if you say that you have a building with only 6 consumers, then what factor are you going to apply? Between 5 and 9, use this one. So if you have only 6, use 0.78. Now let's say if I have these two, 6 and 4, 10 consumers, then I will use 0.63. If you have all of these consumers, 6 plus 4 plus 5, 15, then I will use 0.53. If you have all of these, then you will have 21, use 0.49. If you have another 4 consumers, then you will use between 25 and 29, 0.46. That is what this example would like to say to you. According to how many consumers, each consumer can be an apartment. 1 apartment, 2 apartments, 3. So 6 consumers means 6 apartments. Okay, so depending on number of apartments, we will select the suitable number of consumers downstream. So let's delete this. Okay, so let's say we have this building. What factor I'm going to use? We have how many consumers? 6, 4, 5, 6, and 4. How many consumers? 10, 15, 21, 25. So I'm going to use 0.46. So I'm going to add all of these demand loads, and divide and multiply them by what? Multiply them by 0.46. You can see here, added all of the connected, all of that demand load, not connected, demand load for each panel, 150 kilovolt ampere. Take this one and multiply it by how many consumers? 25.46 multiplied by 0.46. You have gotten the apparent power of the supply or transformer or amount of power needed for the building, 69 kilovolt ampere. You can see there is a big difference between them. Okay, big difference. Why this big difference? Because as number of consumers increase, the possibility of them operating at the same time is much lower. You can see by applying the diversity factor or simultaneity factor, you now have much lower power required, which means very lower amount of very low amount of cable rating and very low circuit breaker rating compared to the 150. Now, as you can see, the diversity factor is applied to every group of loads, different loads such as distribution or sub-distribution, as we have seen in the previous example. You can see here, these are main distribution, then we have sub-distribution that provides two different panels. So at each stage, we apply diversity factors. Okay, great. Now, before we end, we have another one. Let's say, how can we use this in transformer sizing of our building? Now, let's say we have 4 individual feeders with connected loads of 250, 200, 150, and 400. And each of these panels or each of these feeders have a demand factor of 90, 80, 75 cas. Use a diversity factor of 1.5 to size the transformer. Now, first, we have connected loads. First, we convert them or these feeders or these distribution ports into demand load. But how? By multiplying each by their demand factor, right? Like this, 250 multiplied by 90, 200 multiplied by 80, 150 by 75, and etc. Like this. Great. Now what next? Next step is that we will add all of them to get the total demand factor, demand loads, which is 837.5. This is our total demand load. Now if we size our feeder at unity diversity factor, which means all of these loads or maximum loads are always occurring. Okay, or there is a possibility that all of these will have the maximum demand at the same time, which is in reality is not, will never happen. Okay, so it's 37.5. If we size our transformer based on this, you will find that we will look for a transformer for 150 kilovolt ampere if you find it. However, in reality, you will find a 1 megavolt ampere transformer. Okay. Now let's apply our diversity factor, which says that these feeders will never have their maximum demand at the same time. So I will take these, add them together, and divide them by diversity factor to get that diversified load. So divide by 1.5, you can see 558 kilovolt. You can see the difference between them, very large difference between these two. This large difference will lead to lower size of the transformer. So you can see here, for a diversified one, a 600 kilovolt ampere transformer could be used. Okay, compared to what with 150, you can see how much difference between these two. Okay, that's why these demand and diversity factor or simultaneity factor are very important in sizing our transformer, in sizing our cable, in even the load estimation, as we will see in the next lesson. Finally, the simultaneity factor that we use in different buildings. Residential, you will find between 0.6 to 0.7 because we have many customers or lots of apartments. That's why it will be low compared to commercial, 0.6 to 0.8. In industrial, all of the buildings are operating at the same time or having their machines are working, so it will have a high simultaneity factor. And for agriculture buildings, it will be 0.9 to 1. So I hope this lesson was helpful for you in understanding a very important concept in electrical systems, which is the demand factor or and the diversity factor, or simultaneous and coincident factors. Thank you for watching this lesson. I would like to invite you to our academy, Khadija Academy Premium membership, which will help you learn more about electrical engineering. In this academy or in the academy membership, you will find that we'll have more than 100 courses in math, electrical engineering basics, power engineering career preparations. For example, we have electrical design, we have courses on electric circuits, power electronics, ETAB, MATLAB, solar energy, wave energy, wind energy, and much more. You will find also in this academy, you will find the different feedbacks from some of our students that joined our courses. You can, for example, join our membership for just a small fee per month, or you can just have a lifetime access in which you will get all of current courses and classes, and you can have them forever. And not only this, but any new courses that will be created, you will be able to watch it for completely free. So what are the classes that I will learn in this membership? You will find different classes in electric circuits, you will find in transformers, magnetic circuits, machines, power electronics, load estimation, lighting design, lightning also design, earthing system, cables, generators, light current systems or low current systems, off-grid design, on-grid design. Very lots of classes and courses in different topics. Okay, and you will find that inside, when you join this membership, you will find this blueprint that will guide you in which classes you will start with when you join this membership. So thank you, and see you in our membership on Khadija Academy.